everyone, welcome to ExamRat. My name is Shatabdi. I'm a second year medical student. Today we'll be discussing about the topic sound. So in case you've missed out our previous topics, you can easily just go to our website or our YouTube channel and watch it. They're all for free. So let's get started. Okay. So what do we know about this term sound? So we on our day-to-day lives, whenever we travel, we hear various horns of buses, of trains, of cars. We every single, even if it's a small sound like this pen clicking, okay, or the computer shutting down, uh, someone putting on the gas. So all these things, you are able to hear. It's because there are certain vibrations that take place. So basically what happens is that, for example, if you take a car, okay, and the car is honking, okay, so what's happening, and if you are standing here, you're still able to hear the sound, right? So what happens is that here there are, between you and the car, there are thousands of air particles. Now what happens is that when the honking starts, so this causes a difference in pressure between the air particles, as a result of which some come close to each other and some go away from each other, and this causes a motion in the air particles. So this coming close and then going apart, and then coming close then going apart, this whole motion sets in a wave, which ultimately is propagated to your ear. Your ear obviously also has certain particles, which you'll, I'm sure, study in biology. So those particles pick up on the waves, as a result of which they start vibrating, which sends signals to the brain, and then we can process the sound. So for example, if this car is creating a separate honk and there's a bus that's also creating a honk, so you will be able to differentiate between the horn of the bus and the car, because your brain will try to interpret the two kinds of sounds in a different way, and that is how you differentiate between various kinds of noises. Okay, so now let's go over the technical definition. So sound is a form of energy which produces a sensation of hearing in our ears. So you know that in the small classes we've learned about the five senses, the five sense organs, and so hearing was one of them, and that is why it's saying that it produces a sensation of hearing in our ears. Okay, so now, like I told you in the previous slide, that it sets the air particles in motion, right? Which clearly tells us that there has to be some particles between you and the object producing sound, so as to you being able to hear it, right? So what does this mean? This basically means that if you were present in vacuum, like you were standing in space or in vacuum, it means that there are no air particles, right? So even if there's a car, there's a whole drum kit in front of you and it produces noise, you won't be able to hear it, because there are no air particles between you and the objects, and the sound producing objects. So this, what it means is that every sound to be propagated needs a medium. So sound is produced by vibrating objects. The matter or substance through which sound is transmitted is called medium. It can be solid, liquid, or gas. It's very simple to understand it's gas or air, because, like for example, everything around you are hearing because of the air molecules which are vibrating, right? And similarly, if you are in water, you're swimming and someone talks to you, I'm sure you're able to hear it. Whether you hear it clearly or not is a separate issue, but you do hear it, and that means that sound travels through liquid also. Sound travels to solid. The simplest example is phone, right? So the concept here is that, like, not the smartphones earlier, like when we used to have those telephones with long wires. So the concept was that the telephone looked something like this. So anyway, it had these wires. Okay, so now they were basically called optical fibers. So the basically what used to happen is that the sound used to cause motion in the optical fiber particles, which used to lead us to hear the sound or the person talking from the other end. So that also proves that solid can also be a medium for propagating sound. Okay. So here is a simple flowchart. So what it says that the particles do not travel all the way from the vibrating object to the ear, as I told you, like you are not hearing the particles that are coming out of the horn, right? You are able to hear it because the air is a medium between you and the horn. So similarly, the particles do not travel all the way from the vibrating object to the ear. A particle of the medium in contact with the vibrating object is first displaced from its equilibrium position. Okay, so if this is the horn and this is the first particle here, second, third, fourth, fifth, and then there's you. So what it's saying is basically that a particle of the medium in contact with the vibrating object, let's say this particle, it is first displaced from its equilibrium position. If this was its equilibrium position, so now it has gotten close to the second particle, right? It has come here. So now it is basically, it looks something like this. And then again there are the next particles. Yeah. So as a result of which the distance between these two have gotten shorter, it then exerts a force on the adjacent particle, which is particle number 2. As a result of which the adjacent particles gets displaced from its position of rest. Again, this particle will come close to this particle. After displacing the adjacent particle, the first particle comes back to its original position. Okay, so now this you have to understand that as soon as this particle, the second particle basically, comes close to the third one, what happens to the first is that the first is again gone back to its original position. Now, why did it go back? Because I told you that they are vibrating, right? And the term vibration means that they will oscillate among their mean position, but they will always come back to its mean position. It's the same concept as a pendulum, is that it oscillates, but then it again comes back to its original position. So basically what happens is that when it has already transmitted its energy to the third particle, it has lost most of its sound energy, so it comes back to its own position. Then again when the sound energy propagates the sound, then again it will go closer and transfer the energy to the next particle. So after displacing the adjacent particle, the first particle comes back to its original position. This process continues in the medium till the sound reaches your ear. So this process will continue until and unless it reaches your ear. Very simple. Okay. So now we talk about sound as a wave. So let's go over the definition of a wave. A wave is a disturbance that moves through a medium when the particles of the medium set neighboring particles into motion. So as I told you in the previous slide, that the particles are constantly moving, then coming back, again displacing, again coming back. So, and at the same time when it is displacing the other particle, that particle is also vibrating. So it causes a motion, right? So this form of motion, when taken down, when seen as a whole, it forms a wave. So a wave is a disturbance that moves through a medium when the particles of the medium set neighboring particles into motion. Very simple. So again, the particles of the medium do not move forward themselves, but the disturbance is carried forward. As I told you that when one particle moves closer to the other particle, it will transmit the energy which will make this second particle move closer to the third. By the time it has transmitted the energy, it will again come back to its original position. And now this particle has come close to the third one. And that is how again it will come to its original position, and now third one with the fourth one. So the disturbance or the energy ultimately is carried forward, and the particles are then, after doing its job, coming back to its own position, right? So that is why we have visualized sound as a wave, because it works in this pattern. Sound waves are characterized by the motion of the particles in the medium, and hence they are called mechanical waves. Anything that causes motion, that makes a body move or makes a body come back to rest, we know that they are called mechanical waves or mechanical energy, like we had studied in the previous chapter about kinetic energy or potential energy, right? They were together called mechanical energy. Why? Because they were in some way helping a particle move or come to rest or start its motion. So in the same way, we will talk about sound also as a wave, and they are called mechanical waves. So now there are two kinds of waves. One is longitudinal waves and the other one is transverse waves. Okay. So in the previous slide, when I was talking to you about how the particles vibrate about their mean position and then again come back to its original position. So there's a point when the particles are close together, and there's a point they are again far away from each other, right? So this coming close together is known as compression, and this going away from each other once the job is finished is called rarefaction. So it is important because when you plot it in the form of a wave, it will give you a proper sound wave with its proper maximum compression and maximum rarefaction regions. I'll just explain it to you in the form of a diagram. So first, let these be the particles, okay? These be the air particles. So when a sound is being produced, they are coming close to each other, right? So now this is the kind of a picture. So now these particles are compressed. Then again, what happens is that this particle has transmitted its energy. So now something like this is going to happen. So now they are undergoing compression, whereas the first particle has regained its original position. So this portion in between them, this is rarefaction. So this is compression, this is rarefaction. Again, here the particle is being compressed, as a result of which here there is rarefaction. Again, when here there will be compression, here we will be able to see rarefaction. So this is how the waves, the sound wave is propagating. Okay, so if you notice that the motion in the longitudinal waves is forward, ultimately forward, even though they are vibrating about their mean position, they are still transmitting the energy forward, right? So if this was the source of the sound and this is you or the recipient, then the direction of propagation of the sound is the same or is parallel to the movement or the direction of motion of the particles, right? So if this is the direction of propagation of the sound, that is, the sound has to reach from the horn to you, and this is the way the particles are moving, or the particles are transmitting the energy rather, both of them are parallel to each other, right? So in longitudinal waves, the individual particles of the medium move in a direction parallel to the direction of propagation of the disturbance. They do not move from one place to another, but they simply oscillate back and forth about their position of rest. So when you imagine a pendulum, you'll understand that the pendulum is stuck at one place. It's just oscillating and then coming back to its own position. This is exactly how a sound wave propagates, hence sound waves are longitudinal waves. So you have to remember that sound propagates in both solid, liquid and gases in the form of longitudinal waves. So now why are we discussing transverse waves then? We are discussing because in solid sound also propagates through transverse waves. That is because the particles are packed very closely in solids, and it just as well can be transmitted through transverse waves. So what is the difference between longitudinal and transverse? In a transverse wave, the particles do not oscillate along the direction of the wave propagation, but oscillate up and down about their mean position as the wave travels. So it is basically saying that if this is the direction of propagation of the sound, the particles are going to be moving in this manner. So up and down and up and down. So if this is the motion and this is the direction of propagation of the disturbance, then what is the angle between them? 90 degree, right? It's very simple. This is the propagation direction and this is the movement of the particle. So 90 degree, which is perpendicular. So what happens here is, here also the particles are moving about their mean positions up and down, but the direction of propagation of the sound is perpendicular to the direction of the movement of the particles about their mean position. Okay. So you guys can just copy it down. Since I'm going a little fast, you guys can easily just pause the video and note it down at your own space. Okay. Important characteristics of a sound wave. So in the previous slide, we saw how longitudinal waves propagate through rarefactions and compressions, right? So here we are just going to graph it down and form a wave which will be easier for our calculation. So as you can see, this is the portion A is when there was no propagation of sound, right? Because all the particles of air are equally spaced out. In B, you are seeing that some particles are away from each other and some particles are very densely spaced. Then again there is distance, and then again there is a maximum cluster or a maximum dense area. So when taken down as a transverse wave, it gives us this kind of a picture. Here basically what has been done is, the areas of maximum density, like this one and this one, they are graphed as the highest position on the positive scale. Okay, so this corresponds to this area, the maximum peak, and this corresponds to this area. Okay, in the same way, the portion of the least density of the particle has been plotted to the peak but in the opposite direction or in the negative direction, right? So what I was saying was that here the areas of the maximum densities are plotted on the positive side as peaks in the wave, and the areas of minimum densities are also plotted as peaks but in the negative side of the scale. So that is how the wave structure has been formed here. Okay, so where the peak at which it derives its the negative most density is known as the trough. Okay, so this is a trough and this is a trough, whereas this is a crest, which is the positive most peak of the sound wave. Okay, so we have talked about the crest and the troughs. Okay, so if I draw another wave here, just consider them to be equal in magnitude even if it's not. So we get a crest here, a trough here, and then again a crest here. So don't worry, in the next slide we're going to be discussing about the actual definitions of it, and you'll be able to copy it down. So this is simply for your understanding. So here we get a crest and a trough. So now a crest and a trough, they together make up one wave, and the length is known as the wavelength. So the total distance covered by one crest and one trough is called the wavelength. Okay. Now the time taken by this one wave to complete is known as time period. Okay. So the time in which the wave completes one oscillation is the time period. Okay. Now frequency is basically 1 by time period. Why is that? It is because frequency refers to the number of oscillations that can happen in 1 second. So if I say that T means one oscillation taking place, so if it is 1 second, then it is basically 1 by T, right? So this gives us frequency. Okay, so we talked about crests, we talked about troughs, talked about wavelength, time period, and velocity, frequency. So the proper definitions now are that the distance between two consecutive compressions or two consecutive rarefaction is called a wavelength. The time taken by two consecutive compressions or rarefactions to cross a fixed point is called the time period of the wave. The magnitude of the maximum disturbance in the medium on either side of the mean value is called the amplitude. This means that the magnitude of maximum disturbance, it means that this is the amplitude of the wave, or this can also be considered as the amplitude of the wave. Instead of considering just one wave here, while writing the definition, they have considered the distance between two crests or the distance between two consecutive troughs. It is the same as the distance that the sound particle covers in one oscillation. So the definition can be written like this also, that the distance between two consecutive compressions or two consecutive rarefactions is called wavelength. Okay, so this, if this is also lambda, then this is also lambda. Okay, and the time taken for the particle to move from this position to this position is the time period, and the magnitude of the maximum disturbance in the medium on either side of the mean value is called the amplitude of the wave. So this is the amplitude and this is the amplitude. So why do we need to remember so many like terms? Like we've talked about amplitude here, we've talked about frequency here. So why are we talking about this? This is because you measure the sound. When you hear a sound, you basically measure it by three of its properties. One is the loudness, one is the frequency, and one is the quality. So now, loudness basically is dependent on the amplitude. So more with the amplitude, more the amplitude of the sound, more will be its loudness. Yeah. Okay. So if I'm just drawing this, you can understand that this has a higher amplitude than this one. Okay. So even though it does not happen in one single wave, the amplitude will remain constant, but just like as an example, I'm telling you that if you compare this and this wave here, then obviously this is louder. So that is how you understand the loudness of a sound, which is a characteristic property of a sound, by measuring its amplitude. Okay. Frequency. Frequency basically gives us an idea about the pitch of the sound, whether it is high pitch or shrill, or whether it is low pitch or more bass. So basically, frequency, I had told you that how many oscillations can be completed in 1 second, right? So if you consider this wave and this wave again, like 1 and 2, then you'll again understand that here, let us say that in 1 second, these many oscillations are be completed. So in 1 second here, only barely one oscillation is being completed, right? So obviously this has more frequency, as a result of which this has higher pitch. An example of frequency or an example of pitch is that when a bee is making a buzzing sound and a lion is roaring. So obviously the lion's roar is a much more basser sound, so its frequency is obviously very less as compared to the buzz, because the buzz means that the sound is traveling at a very high frequency. That's why you're hearing a very shrill sound. But roar is you're hearing a huge, a basser sound, so its frequency is very less. Okay, quality or timbre, it's basically, it's a qualitative property, it's not a quantitative property, so it can't be defined like the previous ones. Like we have a definition of amplitude, wavelength, and frequency, which helps us in calculating loudness or frequency. But when it comes to quality or timbre, it is basically a qualitative property, it is subjective. So for example, like a very new car and a very old car, their engines will sound different, and that is because the quality is different. Similarly, a guitar and a flute. Okay, so even though their frequencies and their amplitudes are same, still they will differ because they are coming out of two different instruments. So let's just stop this class here. In the next class, we'll continue some discussion about sound and we solve some examples. Thank you.